Year 12, let's have a little look at the written section of your content paper now. So, question 1 asks, monochromatic light of very low intensity is incident on a metal surface. Okay, the light causes the emission of electrons almost instantaneously. Explain how this observation in the first part does not support the wave nature of light. Now, lots of you basically just rewrote what you were actually told, which isn't going to get you any credit. Okay, so let's break the question down a little bit. We know that monochromatic means one wavelength. Okay, we know that the intensity basically tells us how many photons are incident on the metal plate per given area. Okay, so if we have a very low intensity, then for a given area on the plate there are not many photons, okay, or there's not much energy reaching the surface area. It's happening very slowly. Okay, the light causes the emission of electrons, so we know it's the photoelectric effect, almost instantaneously. Okay, so waves, when we have the concept of waves, we know are transferring energy over time. Okay, so the whole idea of waves, before we've started our quantum topic, is that we've got energy in one place and we want to transfer it to another place, and that happens via wave transmission, and energy slowly goes from here to here. Okay, sorry, someone just came in the door. So, now, we know that if it happens instantaneously, it's not happening like wave energy transfer. Okay, wave energy transfer takes time for the energy to get through space, and that isn't happening. So what we want to say for why this observation does not support the wave nature of light is that if we had the wave nature of light acting, it would suggest that if we have low intensity, energy would be transferring to the plate and the electrons very, very slowly. If we don't have much energy with our intensity per unit time, it's going to take a long time for the energy to build up to be enough. Okay, and we're told that it's low intensity, so we know it will be low energy per unit time. Okay, so therefore, because time would be required for the electron to gain enough energy, it's not supporting the fact that we're thinking about light as a wave, because we haven't seen that. We've seen that it's instant. Okay, so you're basically saying, all right, well, why does the fact that it's instant not being asked? Okay, so pause, take a read of what I've said, have a little look at your answer and see how you might change what you've said. Okay, in part II, it asks you, how does this observation that we see support these? The photon theory transferred via waves and the energy building up on the plate. What we have now is each individual photon, so each wave packet, only interacts with one electron. And that energy transfer, because it's a one-to-one interaction, it happens instantly. So because the electrons are now able to instantly absorb a specific amount of energy in one go, and this, which doesn't make sense when you think about waves acting like waves. Okay, and so just pause again. Okay, so in B, you've then got an experiment to demonstrate the photoelectric effect. You've got light that has a wavelength of 480 nanometers and it's incident on a metal surface. So we've got photons coming in here. Okay, they're travelling inwards towards the light, towards the metal surface. So it says the graph shows the variation of the current I in the ammeter with the potential V of the cathode. Okay, so we know that the cathode is a negatively charged plate. Okay, we know that what will happen when light hits this metal surface is electrons will be emitted. Okay, and they will move away with some kinetic energy. Okay, but they are obviously repelled by the negative plate. Okay, this is a negative voltage because it's a cathode, and so this voltage opposes the motion of the electrons. So as we increase the voltage, what's happening is we're slowing these electrons down more and more and more until the point where there's no current flow. The current flow that's being measured by this ammeter is the movement of the electrons that are being emitted, okay? And so what you're seeing in this graph is actually in magnitude, the voltage on this plate here is getting bigger as you go to the left, okay? Although you're obviously going to a more negative number, the negative sign basically just tells you that you're going to get repulsion. It's the magnitude of the voltage that tells you how much voltage we really have, okay? And so you can see that we're increasing the value of the voltage, and that is causing the current to decrease, which makes sense based on what we know. If we increase the negativity of this plate, it's going to repel these electrons more, it's going to cause them to slow down even more. So calculate in electron volts the work function, well, we know that that's psi, of the metal surface. Okay, so we've got our equation that we should have learnt at this point. The work function is going to be equal to the energy given by the photon minus the kinetic energy of the electrons. Okay, I can replace HF with HC over lambda, okay, because I know from waves that C is equal to F lambda. Okay, wave speed is frequency times wavelength. Now, that's important that I do that because the value that I'm given at the top is lambda, not F. Okay, so I'm just replacing HF with HC over lambda. So now we have this new expression to allow ourselves to find the work function. H is the Planck constant, that's a given, it's in your data booklet. C is the speed of light in a vacuum, also given. Lambda is the wavelength of the incident photons, you're given that at the top of the question, 480 nanometers. Okay, so that's the HC over lambda bit. We know that we then need to minus the maximum kinetic energy of the electrons. Now this value is going to be the stopping potential. Okay, so what I want you to think about is that when the electrons are emitted, they have a certain amount of kinetic energy. Okay, as they slow down, as they move closer towards the negative plate, they have gained electric potential energy. That's what the transfer is. They need that potential in order to get closer to a plate that is repelling them. Okay, so we've got a transfer from kinetic energy to potential energy. Okay, so at the point where they are completely stopped at the plate, all of the kinetic energy has been converted to potential energy. Okay, and the way we work that out is by multiplying their charge E by the potential across the plates. Okay, because a charge by a voltage gives you an energy value. And so what we need to look for is the value of the voltage when the current is zero, because if the current is zero, they've transferred all of their kinetic energy. Okay, so all of that original kinetic energy has now been transferred to potential, and so we can see that it's a 1.5 electron volt value. Okay, because each electron has 1.5 volts. And so remember, we're doing HC over lambda minus the maximum kinetic energy. We're going to take our HC over lambda value, which we've worked out. We're going to convert that into electron volts. I'll talk you through that in a second. And then we need to minus the maximum kinetic energy in electron volts, which we've just seen to be 1.5. Okay, so I missed a step, so just very, very quickly. HC over lambda gives you energy in joules. Okay, so this is the value that you get when you plug those numbers in the calculator. But because it's told you that you need to calculate it in electron volts, you're going to need to convert. Okay, so remember that 1 electron volt is 1.6 times 10 to the minus 19 joules. So we're going to divide this by 1.6 times 10 to the minus 19 to find out how many electron volts this is. Okay, so that's a step that a few of you missed. So we get the energy of the photon in electron volts here, we minus the EK max value, which we know is equal to the stopping potential, to get the work function. And that gets us our final answer. Okie dokie. Question 2 then. Suggest why de Broglie's hypothesis is not consistent with Bohr's conclusion the bit in the hydrogen atom has a well-defined radius. This was done well, so really good job because you listened carefully to this. So de Broglie states that an electron is represented by a wave. That was his whole thing, wasn't it? He was looking at electrons or particles acting like waves. So that got you 1 mark. Really, really well done. We're going to skip over part B because you haven't done the wave phenomena topic yet, and this isn't going to make much sense to you. But we'll come back to it at a later point. So the ratio, volume of a nucleus of mass number A, nucleon, is A. Okay, so effectively, whatever this volume of the nucleus is divided by the volume of one individual nucleon gives you is that this ratio implies that the nucleons are very, very tightly packed, or you could have said there's not really any separation space between the nucleus. Okay, that's the observation that I'm making, and that is because the strong nuclear force is greater than the electrostatic repulsion. Okay, so the ratio tells us that there isn't much space between each individual nucleon. Now, given that we know that they should be repelling each other if they're protons, it must be that there's an attractive force overcoming that. Okay, so the strong nuclear force is bigger or dominates over the electrostatic repulsion. That was done pretty well though. Okay, so in part C, you're given a pure sample of copper-64 and told it has a mass of 28 milligrams, and the decay constant of copper-64 is 5.5 multiplied by 10 to the minus 2 per hour. So, because it tells me in the question that I'm estimating activity in becquerel, that is really important to notice. Becquerel is per second. So what that means is I need to convert my decay constant so that it has a consistent unit, so per second. So I know that an hour is 3,600 seconds. So if it decays this many, in all likelihood, so this is the probability of decay per hour, I then need to divide by 3,600 to get the decay constant in per second. Okay? I'm asked to find the initial activity, so that's activity A. I will get that by multiplying the decay constant by the original number of nuclei in the sample. Okay, so this is in your data booklet. This is the equation that you needed to use. The bit that was tricky is that you needed to work out the original number of undecayed particles in the sample. So this is where you use your chemistry a little bit. You've got 28 milligrams, so that's 28 times 10 to minus 3, sorry about that, not my camera. That is the mass. I am going to divide that by the molar mass, or the relative mass I think, which is the 64, that's here, and I'm going to multiply that by the Avogadro number to get the original number. Okay, so we've got the mass divided by the molar mass. We're going to multiply that by the Avogadro number, and that will give us the original number. So, sorry, I've done this in a very scruffy way. Activity is the decay constant, which is here, per second, multiplied by the original number, which is the thing I've just calculated using my moles equation. And when you do that, you get 4 times 10 to the 15. Sorry, I don't think I've explained that very well, but I'm rushing before school starts this morning. So just have a pause, have a little look, come and chat to me or send me a message if you are still a bit unsure. Okay. I've also written the equation properly down here as well. So this equation is what I'm using to calculate N0. Okay. So then it asks you in part II to calculate in hours the time at which the activity has decreased to 1/3 of the initial activity. So this is when you use your second activity equation. So the activity at a time t is given by the original activity multiplied by the exponential function to the power of minus lambda t. So I can rearrange the equation to get A over A naught. So this is the ratio of the activity at a time t compared to the original activity. And I'm told that that must be a third, okay? So activity A must be a third of the original activity. And that then must be equal to e to the minus lambda t. Okay, so I'm taking this and I'm going to take natural logs of both sides so that I no longer have the exponential function to deal with. So natural log of a third, ln of a third, is equal to ln 1 minus ln 3. Okay, if you're not happy with logs, come and speak to me. Ln 1 is 0, so this disappears from the equation. Ln of e to the minus lambda t is just minus lambda t. The minus signs cancel, so I'm left with ln 3 is equal to lambda t. And I'm going to rearrange for t because that's what I'm looking for, the time in hours. Now because it asks for in hours, this time when I do my decay constant, I'm going to do it in per hour so that my value of t will be in hours. So ln 3 over lambda gives us the value of 20 hours. Okay, hopefully this is the almost last question. Fingers crossed I've got time for about 5 minutes. So 3a, the diagram shows the position of the principal lines in the visible spectrum of hydrogen and some of the corresponding energy levels. Okie dokie. Ignore all of my working, that's for later on. It says determine the energy of a photon of blue light emitted in the hydrogen spectrum, and you're given the wavelength in the question. So this is a photon energy, it's hf or hc over lambda. H is the Planck constant, c is the speed of light in a vacuum, lambda is the wavelength of the photon. Okay, here we go, here's my energy value in joules. I did some conversions to think it would help me out later. It ended up not being helpful, okay? But this is the value that you should get. So sometimes IB asks you a lot for 3 marks, and sometimes they ask not very much at all. So don't be baffled if you think it's been too easy, okay? Anyway, this is the value that you get for the photon energy in joules. Notice that the power here is the same as here, okay? So, identify with an arrow for part II, labelled B on the diagram, the transition that gives rise, so causes, the photon with this energy in A. Okay, so you are looking for a transition here that leads to this energy photon being emitted. So we are looking at the difference in energy levels. Okay, to go from minus 0.87 to minus 5.44, I have to have emitted a photon that has an energy of the difference between the two. The difference between the two is the value of the photon that we're looking for. Okay, that's really important. So the transition that you should have chosen should have a difference between these two numbers of the value that you collected here. Okay, because it is a photon being emitted, we know that the energy level of the electron has to have decreased, so my arrow has to point down. So it says explain your answer to AII. Well, firstly, the difference in the energy levels is equal to the energy of the photon, 1 mark. Secondly, I've chosen to point my arrow down because the energy of the hydrogen atom has decreased. The electron has moved from a higher to a lower energy level. So you have to describe why the size of the arrow and why the direction of the arrow. Okay, so you can just pause if you need to make some corrections. Okay, last but not least then, question 4. Oh, sorry, I've got too many bits of paper going on here. Rutherford constructed a model of the atom based on the results of the alpha particle scattering experiment. Describe this model. Describe just means say what you see. Say what the model is. Don't say how we know it. Don't say what Rutherford did to figure it out. Just say what Rutherford says the model of the atom is. Well, he says that the mass, all of the positive charge, is inside of that space, the nucleus, And he says that electrons must orbit the nucleus, okay, up until this point. Okay, that's what you've learned in chemistry before year 12. You're just telling the examiners that you know what that model of the atom is. In part D, you've got radium decaying into palladium. The diagram represents beta minus decay with the arrow. Explain what may be deduced, so what can you work out about the energy of the electron in the beta minus decay. The beta is the electron, okay? And so this arrow representing that decay tells us a lot about the electron. So, first things first, we can deduce the energy emitted in the beta decay. That's the first mark point, the energy release level of the original parent and the final daughter. So you get 1 mark for saying that the energy released is 3.06 megaelectron volts. Okay? Then, a parent decaying to a daughter, plus from the parent that energy is being shared between the beta particle emitted and the antineutrino. That's another thing that we know. So that tells us then that if the energy released was 3.06 megaelectron volts, then the beta particle must have energy anywhere between 0 and 3.06 megaelectron volts, okay, because it can share it in any combination. So it has to be somewhere between those two values, having none of it and having all of it, okay. Suggest why the beta minus decay is followed by the emission of a gamma ray photon. So why is it that once we reach this point, we then need to emit gamma? Well, use the diagram to help you. It is not in its ground state. Okay, a gamma photon is emitted to move the palladium daughter from its excited to its ground state. Okay, so that's all you needed to say here. Pause if you need to copy it out, but I think most of you got that bit, so that was good. And then last but not least, calculate the wavelength of the gamma ray photon in DII. So again, we've got a photon. We're being asked about the wavelength. We're going to use the energy of the photon equation, E is hc over lambda. We're going to rearrange, because that's what we're looking for. We know h, we know c, they're constants, and the energy of the photon must be this difference in energy, okay? Because the gamma photon's only emitted once we've reached this state. We go from this excited state to this ground state to release that gamma photon. So this must be the energy of the photon. Okay, so we know that that energy is 0.48 megaelectron volts. We need to convert that into joules for this equation to work. Okay, so that's why I've taken my amount in megaelectron volts and I've multiplied it by the energy of 1 electron volt in joules. Okay, so we've got hc over the energy gives us that wavelength, giving us your final answer there.